prior couple of chapters have dealt with significance tests that involve means. So now we're shifting to categorical data, and we're going to look at tests that involve samples. And Chapter 19 is going to look at tests for proportions that involve a single sample. So the first test that we're going to look at is the one-sample test of a proportion. That is the one-sample test of P. And this test examines whether a sample proportion P differs by more than would be expected from chance alone from some stated proportion, which is to say some stated value. Now the non-directional pair, the null would state that the proportion in the population from which the sample is randomly selected does indeed equal the stated proportion or stated value. And the alternative would state that this is not so. So in words, the null, proportion in population from which study sample selected equals some given value. Alternative, proportion in population from which study sample selected does not equal the value stated in the null. The hypothesis pair can also be directional, and you can look at the bottom of the slide here to see the two ways that directional pairs can be formed. And again, as always, it is the alternative hypothesis that carries the direction of expectations. And again, we'd only use the directional pair in a situation involving strong expectation. The one-sample test of a proportion calculates a value of z, and here is one of the formulas for it, but basically what one does is take the sample proportion given by the small p and subtract from the sample proportion the proportion stated in the null, and then one divides by the standard error of the proportion to compute z. So here's the formula phrased differently, and you can see here that the standard error of the proportion is computed by taking the proportion stated in the null, p, multiplying times 1 minus p, and then dividing by the sample size. The final step is taking of a square root. And as you look at these formulas, I will simply note that we use the small p to symbolize the proportion stated in the sample. So that's the same symbol that we use for the probability yielded by a significance test. So perhaps it's unfortunate that we use the same symbol, but that's indeed what we do. And indeed, probabilities are proportions. So recall that for the large sample test of the mean and for the different t-tests, there were sample size guidelines that needed to be met for the test results to be sufficiently accurate. Well, for the one sample test of a proportion, results will be sufficiently accurate when both sample size times the proportion stated in the null, and then also sample size times 1 minus that proportion. When both of these are greater than or equal to 5, results are sufficiently accurate. Note that a footnote in Chapter 19 speaks to some situations when this guideline might not be sufficient, and that happens when the value stated in the null is very close to 0.00 or to 1.00. So in our problem example, we presume that in some very large national representative sample of children in school, 10% of children earn we'll just say a score on a measure that conveys serious behavior problems. Now then, in your particular school district, you take a random sample of 200 kids from your district, and you find that 17% have serious behavior problems as indicated by the behavioral measure. So the percentage in your sample, small p, is higher than the large p. I mean, this is going to be the value that we state in the null. So the question is this a large enough difference that it's unlikely to be due to chance? And the one sample test of p can help us reach a decision on this. So we need to implement our hypothesis testing model. Step 1 states the hypothesis pair, and we're going to use a non-directional pair. So the null states that the proportion in the population from which you've selected your children, that is the proportion in the full school district, is 0.10, and the alternative states that this is not the case. Step 2 is the selection of a significance level, and we will set alpha to 0.05. That is to say, we will use the 0.05 level. So the next thing to do is see whether our sample size guidelines are met. I mean, in essence, we need to see whether both n times p and n times 1 minus p are greater than or equal to 5. So n equals 200, p equals 0.1, np computes to 20. N times 1 minus p equals 200 times 1 minus 0.1, that is to say 200 times 0.9, and that computes to 180. So it is indeed the case that both np and n times 1 minus p are greater than 5, and as such our test results will be highly accurate and we can proceed with that test. Step 3 is carrying out the formula. I think the easiest way to do this will be to calculate the standard error of the proportion, and then we will insert that into the denominator. So here is our calculation of the standard error of the proportion. P times 1 minus p divided by 200, and we come across, we've got 0.09 divided by 200, and we need to take a square root, and that is going to calculate to a standard error of the proportion of 0.021. So that's what we need to plug into our formula. That's our denominator. Here's our small p, 0.17, the proportion in our random sample. Here's the large p, the value stated in the null, and we get a z, an obtained z of 3.3. Now step 4 is to make a decision on the hypothesis pair. It is the case that the decision rules for the one sample test of the proportion are exactly the same as are those for the large sample test of x bar. So all of these decision rules are stated in chapter 15, which covers the large sample test of x bar. Now, for a two-tailed test where alpha equals 0.05, the decision rule calls for rejection if the absolute value of the obtained z is greater than or equal to 1.96. 3.30 is our obtained z, and the absolute value of 3.30 is 3.30. That is indeed greater than 1.96. So, following the decision rule, we reject the null. We conclude that the higher level of behavior problems in your school district sample is unlikely to be due to chance alone, and therefore presumably in the full population of children in your school district, it is unlikely that the null is true. It's unlikely that the proportion with serious behavior problems is 0.10. Here's a visual look at our results. Note that 0.10 is the mean of the sampling distribution. That's the value stated in the null. The standard deviation which is the same thing as the standard error of the proportion. It is 0.021. So 0.121 minus 0.100 is 0.021. So you can see that our study sample result of 0.17 is more than 3 standard deviations above the mean. Here are the rejection regions, and our result is way out in the tail of the upper rejection region, and we do indeed reject the null. So we're going to move on to a new test that's also used with proportions and with a single sample, and that test is the binomial test. And the binomial test addresses precisely the same question as does the one-sample test of P. And that question is, does the proportion in one study sample differ significantly from the proportion stated in the null? The binomial test is often used with small samples. In other words, its very important use is when the guidelines for the one sample test of the proportion are not met. So when either np or n times 1 minus p is less than 5, that's an excellent time to use the binomial test. The binomial test is based on the binomial distribution. We encountered the binomial distribution first in Chapter 12 when we learned about sampling distributions, and we encountered it again in Chapter 14 when we presented sampling distributions involving flips of a coin. The binomial distribution yields exact probabilities. It's really a point that you don't have to know, almost technical one. The one sample test of P yields highly accurate probabilities, but they can differ by small amounts from the exact probabilities, and these differences are negligible when sample size is sufficient, as conveyed by adequate values of np and n times 1 minus p. Basically, the binomial test is a good test for small samples. Many computer software packages routinely carry out the binomial test. And the hypothesis pairs are just the same as those for the one sample test of P. For reasons that are covered in the text, except when the value stated in the null is 0.50, interpretation of two-tailed results, which is to say results from non-directional pairs, can be problematic. So we are only going to cover one-tailed directional tests here. And further, I've mentioned to you that this test is often used with small sample size. With small sample sizes, power is often low. And that being so, this text only demonstrates the binomial test where the significance level is 0.05. Use of the 0.01 level makes rejection of the null more difficult, and with small sample size, it's often a good idea to stick with the 0.05 level. If sample size is sufficiently small, one might even want to use the 0.01 level. Now, we are going to use a binomial distribution table. There are going to be no calculations involved as we carry out this test. In future classes, you'll use a software package to carry out the test, and you'll get an exact probability. And we're not going to get exact probabilities from the table that we reference. So we are going to stick with the same content area as for the one sample test of P example. We're going to stick with behavior problems. And so we've already mentioned that 10% of children in a very large national representative sample experience behavior problems as indicated by some instrument. Now here, rather than having a random sample of size 200, you have a random sample of 5 kids from your school district. Step 1 is to state the hypothesis pair, and we are going to use a directional pair for all examples in this text with the binomial test. And our alternative is stating that large P, which is to say the proportion in the population of children in your school district, that proportion is greater than 0.10. Step 2 is to select a significance level, and we are always going to select the 0.05 level for the binomial test. Now let's present the test results visually, that is via the sampling distribution, so that if you selected a random sample of size 5, and if in that random sample the proportion was 0.10, what is the distribution of results that you would get if you selected an unlimited number of random samples? Now here I'm presenting results in terms of coin flips, but the same logic would hold for behavior problems. About 59% of samples you would get 0 behavior problems, or 0 heads as the case may be. You'd get 1 head in about 33% samples, 2 heads in about 7% of samples. You would get 3 heads in a little bit less than 1% of samples, and for 4 and 5 heads, or we could think in terms of 4 or 5 kids with the behavior problems, you would get those results very, very rarely. Well, let's go ahead and calculate the probability of getting 3 or more heads, or we can say 3 or more kids with behavior problems. We would sum the probabilities for 3, 4, and 5, and so the exact probability of getting 3 or more heads would be 0.00856. So we would get 3 or more heads a little bit less than 1% of the time. And indeed, the probability of getting 3 or more heads is a little bit less than 0.01. Now, you're going to carry out problems for the binomial test by referencing a table in the back of the text. So we've got a portion of that table presented here. The headers for the columns convey different proportions that might be stated in the null. Now the proportion stated in our example is 0.10, so that's the column that's going to apply. The far left column indicates sample size, and as you know, n equals 5 in our example, so this is the row that's going to apply. The second column states the direction stated in the alternative. So in our example, the alternative states greater than. So the number in the table that's of interest to us is the number in the 0.10 row for sample size 5, alternative stating greater than. Now, having seen how we reference the appropriate number in the table, I need to go ahead and state for you the decision rules. When the alternative states greater than, the decision rule calls for you to reject the null when the frequency in the sample is greater than or equal to the frequency in the table. So in our example, the frequency in the table is 3. Our sample frequency was 3. In other words, 3 of the 5 kids had behavior problems. And our sample result is indeed greater than or equal to the frequency in the table. I mean, 3 obviously equals 3, and therefore we reject the null. So we can conclude that the difference between your study sample results, I mean, in essence, 60% of kids had difficulty with behavior in your sample, and the proportion stated in the null, which was 10%, that difference is unlikely to be due to chance. And you would, on the basis of these results, conclude that it is unlikely that the proportion in the full population of kids in your school district who have behavior problems is 0.10. And this is a one-tailed test, so indeed you would conclude that it is likely that the percentage who have behavior problems is greater than 0.10. In other words, you're accepting the alternative hypothesis. Now let's talk a little bit about statistical power. I mean, I've already mentioned that given that the binomial test is often used with small samples, power is often low. Now note that sometimes there is no number in a given cell in this table. So for instance, when the null states 0.5 and sample size is 4, there's no number here, and similarly there's no number in the greater than row either. As another example, when sample size is 4, and look, here are four columns, and we see for these 4 proportions blanks in where there should be numbers. So and here again are some more cells of the table that are blank. So what are these blanks conveying? So blank in the table is conveying to you that no study sample result, that is, no obtained frequency, will result in rejection of the null. So that, I mean, suppose that you had a sample size of, say, 4, and that the proportion that you stated in the null was 0.5, and we can let you carry out a directional hypothesis in either direction. Well, whatever the result you might obtain, whether you might get, and I'll stick now with the behavior problems example, you might potentially get 0, 1, 2, 3, or 4 children with behavior problems. It is the case that none of these results, that is, none of any of the possible results that you might obtain, because obviously you've got to get 0, 1, 2, 3, or 4 kids with problems if you're testing 4 kids. So no results are going to be statistically significant. No results are going to reject the null. The probability of obtaining any given result or a more extreme result, the probability of that is due to chance is greater than 0.05 for all of the different results that one might obtain. So in this situation, your statistical power equals 0. You simply have no opportunity to reject the null. In such a situation, in essence, there is no reason to carry out a significance test. Now, one thing that you might do is set alpha to 0.10 rather than to 0.05, perhaps. Or perhaps increase your sample size so that you at least do have some statistical power. And we do need to consider the situation where the alternative states less than. Our prior example was one in which the alternative stated greater than. So the decision rule when the alternative states less than is to reject the null when the frequency in the sample is less than or equal to the frequency in the table. So here's another example. Your null states that the proportion in the population is greater than or equal to 0.50. Your alternative states that the population proportion is less than 0.50. Your sample size is 6. The frequency that you obtain in your sample is 1. So in this example, the sample frequency of 1 is greater than the frequency in the table, and that's 0. So here's the appropriate cell. So as the sample frequency is greater than or equal to the tabled frequency, you reject the null hypothesis and accept the alternative. And let's just do one more example. Let's do another behavior problems example, and let's do an example in which the alternative is going to state greater than. So suppose that the population proportion is hypothesized to be 0.25. So in this situation, our null would state p is less than 0.25, and our alternative would state p is greater than or equal to 0.25. We have an n of 6, and suppose that we find 4 kids with behavior problems. We'd come over here and find that the tabled number is 4. We obtained 4, so indeed the frequency that we obtained is indeed greater than or equal to tabled frequency, and in this situation we would reject the null. We're going to cover the one variable chi-square test in the next video.